Welcome. So you've probably wondered how you find the area under a curve when it's not a simple y equals f of x situation. Well, today we're going to dive into the really elegant world of parametric curves and get the tools to do exactly that. So here's our game plan. We're going to start with the basics, the stuff you already know. Then we'll adapt our tools for parametric equations, and finally we'll work through some pretty cool examples. Ready? Let's jump in. All right, so we're all familiar with using a definite integral to find area. It's classic calculus. But what happens when our curve is defined by some parameter? Let's call it t. How in the world do we adapt our familiar formula to handle this kind of new dimension? Well, the solution is actually a really clever substitution. It lets us do all of our work entirely in the world of our parameter, t. We're not going to reinvent the wheel here. We start with what we know best. The entire key to solving this thing lies in transforming this one fundamental expression. So, how do we actually make the switch? Well, first up, we substitute y with its parametric form, g of t. Simple enough. For dx, we use the chain rule, which lets us express it in terms of t, giving us f prime of t dt. And of course, we can't forget the limits of our integration. They have to be converted from x values to their corresponding t values. And voila, here it is. After substituting our y and our dx, we get this new, powerful formula. This is our new workhorse. This single expression lets us calculate the area for pretty much any parametrically defined curve, all in terms of t. Okay, before we get our hands dirty with some examples, there's a super crucial point to remember. This is one of those things that can really save you a lot of trouble on an exam. You have to pay attention to the direction your curve is being traced. If your parameter t traces the curve from right to left, you're going to get a negative area. But don't panic, it's an easy fix. Just flip your limits of integration or take the absolute value of your final answer. All right, enough theory. Let's move on to our first example and see how this thing actually works in practice with a shape we all know and love. We're going to find the area of this ellipse. So first things first, we need the derivative of x with respect to t, which is just negative 2 sine t. Now, to make our lives easier, we're going to use the ellipse's symmetry. We'll just find the area in the first quadrant and then multiply our final answer by 4. Easy. So now we plug our y and our dx into the formula. This gives us the integral of negative 6 sine squared t. And here's a really neat trick. We can just flip the limits of integration, and that cancels out the negative sign, which makes our integral much cleaner to work with. Now, to solve this integral, we can't really work with sine squared t directly, so we've got to pull out a classic power-reducing identity. This is definitely one you want to have in your back pocket. It lets us replace sine squared t with something we can actually integrate. Okay, with that substitution in place, now we can integrate. The integral of 1 is just t, and the integral of negative cosine 2t is negative sine 2t over 2. Now we just have to evaluate this at our bounds. And our result is 6 pi. Now, what's so great about this is we can actually check our work. The standard formula for the area of an ellipse is pi times a times b, which in our case is pi times 2 times 3, or 6 pi. It matches perfectly, so our new method totally works. But what about a curve that doesn't have a simple known area formula? Now that we've built up some confidence, let's tackle a more complex and honestly a more beautiful curve, the cycloid. This is the path that's traced by a point on the rim of a rolling circle. It's pretty cool. So we're given the parametric equations for one arch of the cycloid, where r is just the radius of the circle that's generating it. We're going to follow the exact same process. We find dx dt, and we set up our integral by substituting in y and dx. This actually simplifies pretty nicely to r squared times the integral of 1 minus cosine t squared. To integrate this, we first need to expand that squared term. And look who it is again, our old friend, the power-reducing identity. This is the key to moving forward here. We'll just substitute this expression in for cosine squared t. Okay, after we substitute the identity and simplify, we can integrate each term. Then we evaluate from 0 to 2 pi. And notice how awesome this is. The sine terms all go to 0 at both limits, which makes our final calculation way easier. All right, we did the hard work. We navigated the derivatives, the integrals, the trig identities. Now it's time for the payoff. And honestly, it's a truly elegant piece of mathematics. The final answer for the area under one arch of the cycloid is 3 pi r squared. And this is the beautiful part. Just think about that for a second. The area of the little circle that generates this whole curve is just pi r squared. Our result, 3 pi r squared, means the area under this arch is exactly 3 times the area of that circle. It's a completely unexpected and perfect relationship. It just leaves you wondering, what other elegant connections like this are just hiding inside the formulas we use every day? And this really matters because calculus doesn't just give us answers, it reveals the deep, often surprising, and beautiful structure of the world all around us.